Thank you very much for the invitation and the opportunity to speak here. So yeah, I'll be discussing this topic, and everything will be joint work with Ramon van Handel that I'll speak about. So I think first I'll just explain two perspectives that we can have on vector-valued concentration inequalities, which will be the main type of result that I'll discuss in this talk. So the first perspective that we can have is as generalizations of classical concentration inequalities, like the Poincare inequality, which we can think about as results from high-dimensional probability, and we can ask the question, we have many such results for different measures for functions that take values in R or in Euclidean space, but how can we generalize these results for functions that take values in a general Banach space? So that's one perspective that we'll have. But the other one, which you'll see from some of the applications that I discussed, is that we can also see these probabilistic results as functional inequalities that tell us something about the properties of Banach spaces, and in particular, metric geometry. So some of the applications that I'll discuss later have to do with embeddings of discrete metric spaces into Banach spaces, and so we can kind of view these results from two perspectives. On one hand, as probabilistic results that say something about high-dimensional random structures and how they behave in a vector-valued setting. On the other hand, these results also have applications in analysis where they say something about the structure of metric spaces and Banach spaces. So as I said, there are many classical concentration inequalities in the scalar valued setting. We have Poincare inequalities, Lox-Sobolev, but in the vector valued setting, there are many fewer examples. So I'll just go over two classical results by Pizier. So the first theorem from 1985 by Pizier is on Gaussian space. So if we take X to be a general Banach space, and we consider a function f going from Rn to x, and we take G and G prime to be independent standard normal random vectors on Rn, which are independent of each other. Then if f satisfies some locally Lipschitz property, Pizier showed the following result. For t between 1 and infinity, we have that the concentration of this function f on our Gaussian space is bounded by some constant times the expectation of independent Gaussian coefficients times the gradient of this function, essentially. So we can see this as some Sobolev type inequality that we consider the concentration of this function with respect to the Gaussian measure in Rn, and one can bound it by some linear quantity, which is the gradient dotted with independent Gaussian coordinates. And so one of the important features of this inequality is that there's a dimension-free constant, which is always desirable in these high-dimensional settings so that we can get good bounds as n goes to infinity. So in the same paper, Pizier proved a directly analogous result on the discrete hypercube, and this will immediately show some of the issues that arise when we try to take this result to the discrete setting, because the proof of this relies very heavily on special properties of the Gaussian distribution, such as rotational invariance, and so the proof does not generalize easily. It's very special to the Gaussian setting. So again, from the same paper, he proved an analogous result, but now we consider functions that go from the discrete hypercube, so the set minus 1, 1 to the n, in Banach space X. And if we let epsilon and epsilon prime now be uniformly distributed on this set, then he proved a similar inequality, but with a worse constant. So we have that the concentration of our function f, now with respect to the uniform measure on this set, is bounded by, so we have log n to the p, expectation of an analogous term to this one, but now we have discrete derivatives, which I can define more precisely later, but we just think of them as differences across the edges of this graph if we consider it with the Hamming metric. So you can see that in this setting, he got constant log n, and this was shown by an example of Telegrand in 1993 to be sharp. So we cannot do better than log n in this setting, and this kind of put a roadblock on considering inequalities of this type, because, as I'll explain later, this inequality, if it were proved with a dimension-free constant, would have important implications in the theory of embeddings of metric spaces in Banach spaces. But yeah, so further work in this area consisted of putting assumptions on the Banach space in order to be able to prove similar inequalities with dimension-free bounds. But we can ask the question, instead of trying to put assumptions on the Banach space, can we think about inequalities in a different way, prove inequalities in a different form that would give dimension-free constants and give us the applications that are desired in this setting? So that was shown in a result from 2020 by Ivanisvili, Van Handel, and Volberg. In the same setting on the discrete hypercube, and I'll write down the inequality, and it looks a bit more complicated, but I'll explain all of the pieces. So we're in the same setting where we have a function from the discrete hypercube to our Banach space X, and again, epsilon is uniformly distributed on this set. Then for p between 1 and infinity, they again show this inequality. So I haven't defined several objects on the right-hand side now. So first, let me define these discrete derivatives more precisely. So we simply define dj of f on the hypercube as the difference f of x minus f with the sign of the jth coordinate flipped. So instead of xj, we put minus xj, and there's some normalization 1/2, which is not very important. And this measure, mu dt, is simply a probability measure on the positive real line, and again, it's more for just aesthetic renormalization of this result. So the important quantity here are these coefficients delta jt, which I will not write down the precise form of, but it'll make more sense later in the talk. And these are some rescaled Rademacher random variables. So in the inequality by PZA, analogously to the Gaussian result, he put random coefficients which were uniformly distributed on the discrete hypercube. And in that case, we cannot get a better constant than log n. So the main idea here was that by putting some random coefficients, which are still discrete random coefficients, in this setting, the deltas are independent of epsilon, and they're also independent across the coordinates j. But there's some rescaled distribution by this parameter t, which we're integrating over. And this gives precisely a dimension-free bound, which gives the desired applications in the setting of Banach space theory.
And sorry,
Yes.
this result of PZA, if you have assumptions on x, then you get rid of the log, right?
Yes, so I'll discuss it a bit later, but if you make assumptions about the Rademacher type of the Banach space X, then you can show that you do not need the log n factor.
Like if you don't have L infinity n's uniformly.
Yes, exactly. So if you have any copies of L infinity, that was exactly the counterexample by Telegram, that if you have any copies of L infinity embedded in your Banach space, then you get this constant log n, but otherwise you can prove the inequality with the dimension-free bound. And for example, papers by Asaf Noor and Shechtman, they show that if you have, say, like a UMD assumption on the Banach space, so something about martingale increments in the Banach space, then you can also get such inequalities with dimension-free bounds. But we're interested in the setting where you do not assume too much about the Banach space, and then you can still get an inequality with dimension-free bounds. Any other questions? Okay, so in my work with Ramon, we're interested in generalizing these results to more general settings than the discrete hypercube, because again, in this case, it relies very heavily on the fact that the hypercube has a product structure. You get a lot of independence from this, and you can write down the distribution of these random coefficients exactly, and they're very simple to operate with. But as soon as we go to more general settings, a lot of these nice properties start to break down, and then we have to use some other techniques. So that's what I'll discuss now, the setting on general groups. I learned that I'm supposed to erase. So I'll describe a bit the setting, and we use a Markov semigroup argument, which will explain where there's weird coefficients and the integral is coming from inequality. So in general, we'll work on GS, where G is a finite group, and S is a symmetric generating set of the group, which means that if we have some element S in the set, then S inverse is also in the set. So this will give us some reversibility condition for the semigroup. And I'll denote mu as the uniform measure on this group. And similarly,
I'm sorry, so what exactly is a symmetric generating set?
This means the condition that if we have some generator S in our set, this implies that S inverse is also contained in the generating set. So what we'll see later is that we'll have a random walk on this group, and this condition will give us that the random walk is reversible, so we can reverse time and have the same distribution.
But is it minimal such set?
Sorry?
S is minimal?
No, it can be any generator set. So for example, the main result that I'll discuss later, we take G to be Sn, so the symmetric group, and the generator set that we'll consider is all transpositions ij. So all permutations that just take two elements and switch them.
But all transpositions, they generate permutations.
Yes, but it's not a
This
minimum.
definition doesn't make sense. Like, why would it generate all elements in the group? Just if you assume SNS implies this inverse of S.
No, she was explaining.
But this is what it means to be a symmetric generating set.
What's a generating set? It generates a group.
Yes.
Okay.
So generating set means that we can get, for example, in this setting, all permutations as a composition of these transpositions. And for example, this is not the smallest generating set that we could take because we could take much fewer transpositions and still generate the entire group. But I think you'll see later on why we consider this example. And it's actually interesting to consider different generating sets. So for example, in Markov chain mixing theory, there's an entire area where people study the symmetric group with different generating sets and how does the random walk mix depending on the generating set, etc. So it is interesting to consider these different settings. Okay. So again, we can define a notion of discrete derivative, which we can think about as the graph derivative on the Cayley graph of this group, or we can define it simply as f of x minus f at the point x with one of the generators s applied. So we have a directional derivative in the direction of each one of the generators of the set. And in this case, we can define the Laplacian on this group as minus, because I'm a probabilist, the sum over the generators of these derivatives. And formally, we can write that this Laplacian generates a heat semigroup PT, which is what we will use to interpolate between symmetries.
And this is really second order differential operator.
Yeah, so one interesting aspect of the discrete setting is that first order differential operators are equal to second order differential operators. So this is something like very discrete, obviously. So that's why we have one derivative, but this is actually equal up to constants with the same operator with second derivatives or even higher order. So this is something very strange that happens in the discrete setting, and we can actually exploit this in some settings. So now I'll write down the definition of these strange random coefficients delta t, and they actually are written in terms of the heat kernel of the semigroup. So if we define little ptxy as, okay, so I guess I skip a step. So we can express pt in terms of a random walk on the group. So if we take a continuous time random walk on our group, by which I mean the random walk starts at some point in the group, and every time a Poisson clock rings, we choose a generator uniformly at random, and the random walk jumps to that next point in the group. So we can express the semigroup PTF of x as the expectation of this random walk at xt evaluated by the function f, given that our random walk started at the point little x0. So this is a standard definition. Yeah.
So if you consider the integer lattice, then the group will be like the cube.
Mm-hmm.
Right.
Yeah, so you can consider the discrete hypercube as a product group, and this will be a generalization of that setting.
Okay.
Okay, so we'll define little ptxy to be the probability that our random walk is at the location y, given that at x0 it started at little x. So then the definition of these delta coefficients, which are indexed by the generating set, is this difference quotient of the heat kernel of the random walk. So here, again, it's some discreteness coming out, but we can think of this as the gradient log of the heat kernel of PT, where we're substituting the discrete notion of derivative. So now with these preliminaries, we can write down a general analog of the inequality I wrote down before, but for any group. So the result is that we can bound the concentration of our function f, so a vector valued function on this group according to the uniform measure on the group, by 1/2 the integral of the sum of these random coefficients delta st, which are arising from the heat kernel of the semigroup, times the derivatives ds f of x. So in this case, we have a general result, but we can immediately ask the question, like, is this useful out of the box? And it turns out that you need to do a lot more to apply this result in any setting. So the first issue that we have is that in the case of the hypercube, we had that these random coefficients were independent across the indices, but for a general group, we'll see even in the case of the symmetric group, one does not have this independence. And now we are dealing with a sum of dependent random coefficients. Yeah, do you have a question?
So, I mean, delta is also a function of x, right? Unlike in the hypercube setting.
Yes. Okay. Yeah. So in the group setting, it turns out that this is actually a function of, like, it depends in a univariate way on x inverse, so it's actually independent of the starting location. But yeah, it's a bit easier to write it in this way. So yes, so one of the first main issues that we have to deal with is that we do not have independence of these random coefficients, and so we're dealing with the sum of vector valued elements multiplied by some dependent random coefficients, and most of our work has been to try to control this sum. So I can write down the...
I'm sorry, so
Yes.
the S of t is only plus minus 1, or is it also this?
So they're a discrete distribution, but yeah, so our intuition is that there are some discrete variables with Poisson-like tails. So it's some discrete distribution that's rescaled by t. But like in principle, it can take as many values as one has elements in the group. So I guess I can write the further result that we have here. So, all right, actually I'll write a definition first. So for the result on the symmetric group, which is the setting where we're able to have some useful bounds on these delta random variables, we also have ideas for other settings, but this is the main result right now. We make an assumption on the Rademacher type of the Banach space, and we get a nice inequality for all spaces that have non-trivial type, which I'll define now. So we say that a Banach space X has Rademacher type P between 1 and 2 if for all elements x1, xn, and x, which are simply deterministic elements, and epsilon 1 to epsilon n, independent Rademacher variables, so random signs which are plus or minus 1 with probability 1/2. We say that the space has Rademacher type P if it satisfies the following inequalities. So the expectation of the sum of these elements of the Banach space multiplied by random signs to the power P is less than or equal to some constant times the sum of the norms of these elements in the Banach space. So what's the intuition for this definition? So for first, all Banach spaces have type 1. So you can see that if you put p equals 1 in this inequality, this will simply be the triangle inequality, so we call this case trivial type. The other end of the spectrum is that Hilbert spaces have type 2. And furthermore, all LQ spaces, so either little LQ or functional LQ spaces, have type Q for Q between 1 and 2. So we can think of Rademacher type as kind of some measure of how close a Banach space is to being a Hilbert space. This is not precisely true, but it's the general idea. So given this definition, we can formulate the following theorem on the symmetric group. So again, our setting is the permutation group with the generators being all transpositions ij. And for any function going from this group to x, where x is of type p between 1 and 2, we have that the concentration of the function is bounded up to some universal constants by log n over n to the 1 minus p times the expectation of these derivatives of f, where I've indexed them by ij because each of our generators is some transposition ij. So as you can see, in this case, we get a constant which is decaying with n, and as I'll explain in a moment, this is the correct constant, which is predicted by some results in this embedding theory of Banach spaces. But just to make this a bit less abstract, I wanted to give a few examples of functions f which one could consider, because one can ask, okay, what is some like vector valued function on the symmetric group, which is interesting. So this is also an area that I'm still thinking about like different probabilistic applications of these results, because right now we've been mainly aiming towards these embedding results, which is good because there's some conjecture of what's the right constant that one should get. But I think there are also a lot of probabilistic applications that are interesting to consider. So some examples that exist in the literature is that one such function, f of sigma, is the cycle structure of the permutation. So one way of defining this is that for a permutation, we can uniquely decompose it into its cycle structure. So for example, we can write, 5, 6, 1, 3, 4, 2. So we see that this permutation has one cycle of length 1, one of length 2, and one of length 3. So for any permutation, we can consider the vector valued function, which takes the permutation to an ordered list of the size of its cycles. And this is a quantity which is of interest in the literature. We know, for example, which distribution this follows for uniformly distributed permutations, but one could ask questions about how does the LQ norm or different norms of this quantity scale. So the other example.
So what's the Banach space?
Sorry?
What's the space?
Okay, there is some rescaling you have to do, but I think I don't want to write down the details because it's a bit technical, but one can consider the list of the cycle lengths in decreasing order, then one can renormalize it by the expected size of the largest component in some Erdős-Renyi random graph, and then this will converge to a simplex, basically.
So the space is a ren, and this would be vector 3 to 1.
So it'll be a discrete space, and you can consider the LQ norm on that space. So, for example, you can consider it as belonging to the space minus, or
subset
to
of
the n, and then you can put any norm on this, like an LQ norm, L1, L2.
So what is this H of sigma exactly? I'm sorry.
So this is the cycle structure of sigma.
But it's a real number, or
So it's a vector in a ren.
Yes.
Oh.
That
So
has degrees and coordinates and stuff.
Yeah. So I don't want to write down the whole definition, but this is what it is.
So in this example, that you give.
So here you would have 3, 2, 1, and then you just formally put zeros because you have one cycle of 3, one of 2.
Okay.
So the other function that one could consider is that for any permutation sigma, one can take the matrix representation of sigma. So you would have some n by n matrix. So this would be some element of the set 0, 1 to the n, or to the n times n, and then one can consider any function of this matrix and bound its concentration. So those are just a few examples of vector-valued functions that could be of interest. Now I'll talk a bit about the application of this result for Banach embeddings, and then if I have time at the end, I'll make a few comments about the proof and some of the techniques relating to semigroups that we use.
So if you apply your theorem to one of these two results, what sort of conclusion do you get?
So that's something that I'm interested in working on right now. So one of the directions that I'm interested in is to, one of the things that I haven't mentioned yet is for the proof we interpolate between this function f and its expectation using the semigroup. So we can also write down a result that expresses some ergodic behavior by, instead of interpolating between p0 and p infinity, interpolating between pt and p infinity, and this gives us some vector valued bound on the behavior of the concentration of this function. So that's something I'm interested in working on right now, but I don't have concrete results in that direction at the moment.
But you mentioned something about this Enflo result or Enflo conjecture.
So that's what I can explain right now is the application of this result in the space of embeddings, which is a similar type of result to this Enflo conjecture, but for the symmetric group, which is an open problem. So first, I'll define by Lipschitz embedding. So we say that a function from some metric space M. So in this case, we'll consider, for example, the Cayley graph of the symmetric group with the generating set of all transpositions. Or we can think about it as a group with the word metric on that group. So how many generators do you need to express any element to some Banach space X? So we say that this is by Lipschitz embedding with distortion B. If there exists some constant little d such that I should use little c here is less than or equal to so this is also called multiplicative distortion. So basically what we are saying is that this function f going from our metric space to a Banach space, that it does not distort distances too much in a multiplicative way of thinking about too much.
But so this has so far nothing to do with the symmetric group.
So in our case, we'll take MD to be Sn.
Oh, okay.
So the corollary of this theorem that is still up there is that for any f going from the symmetric group where S is the set of all transpositions to a Banach space X of type P between 1 and 2, so that the distortion of f is lower bounded up to universal constants by n to the 1 minus 1 over p times some log factor, which we believe is like a technical artifact of the proof. So this does not change the qualitative result, which is that for any p larger than 1, so for any Banach space of non-trivial type, we cannot embed the symmetric group with high fidelity into a Banach space. So since we show that this distortion is growing unboundedly with n.
Sorry, what's the metric there on Sn exactly?
Okay, there are different ways of considering it. So one way we can think about is the word metric on the group. So if we have two elements in the group, then one way to define the metric is how many transpositions do you need to get from the element x to y. Or equivalently, you could draw the Cayley graph of the group. So you draw a graph where you connect each x to Sx for all x. So actually one of the properties of the symmetric generating set is that this will give you an undirected graph, and then you can simply consider the metric on that graph where each edge has a weight 1 in the metric, and yeah, in the typical sense.
But so the metric is dependent on your set of generators.
Exactly, yeah. Any questions about this? So since I have a bit of time, I can say something about the proof. So, what do you think I want to say? So I guess I was not very smart because I just erased the result, but yeah. So the first main idea of the proof is not new. It's using an interpolation technique with the Markov semigroup, and this was already in this paper from 2020 of Ivanisvili, Van Handel, and Volberg, that we use the Markov semigroup on the group in order to interpolate between the two quantities on the right-hand side of the inequality. So here we can see this as we're trying to bound the difference of the norm between this quantity and this one, and we can exactly use the semigroup PT in order to do this, where we use the property that P0 of F is equal to F, and P infinity of F is exactly the expectation of F. So one way to see it would be that we have that our random walk on the group will converge to its stationary measure mu, which is the uniform measure on the group. So we have this ergodic result. And then by applying the fundamental theorem of calculus, we get that this difference, f minus its expected value, is exactly the integral the derivative of our semigroup, and by the Kolmogorov equation, we can write this in terms of the Laplacian of the group. And at this point, we apply the key lemma, which is where these delta coefficients arrive naturally, that we can write ds/pdf. So recalling that our Laplacian is defined in terms of these derivatives ds. This is exactly the expectation of f of xt times this random coefficient. And if you do the computation, you see immediately why this strange quotient derivative of the heat kernel is appearing. So this is where these delta STs arise in the proof. And now, as I mentioned, the main difficulty in the setting on the symmetric group is that we do not have independence of these delta STs. So we have to use a variety of techniques. First, in order to apply the assumption of Rademacher type, and second, to control the moments of these random coefficients. So the step one of the proof is to apply Rademacher type. Okay, I guess that I also erased, but we can recall that Rademacher type has to do with sums of elements in the Banach space multiplied by random signs. So the main question is, how does one insert these random signs into the expression which we have on the right-hand side, which, if you recall, was some expectation of this form. So for this, we actually used some techniques from high-dimensional probability. So the main one is symmetrization, which classically is for sums of independent random variables. If these variables were independent and mean 0, then up to a constant, one can simply insert independent Rademacher signs here to get an upper bound on the original quantity. But in our case, we do not have independent variables, so we cannot do this as easily. But the property that we exploit is that we actually have exchangeability of these random variables, and this comes from some special property of the generating set that we chose, that this is an entire conjugacy class of the group. So we use that, so these delta STs are exchangeable, meaning that using the property that the set of transpositions is a conjugacy class of the group, we see that the action of the group is acting as a permutation on the generating set, and this allows us to get exchangeability. So the fact that this distribution is invariant under permutations of the generating set.
So at this point, you also need this kind of symmetry that you demanded. I forgot how you call it. I mean, it's symmetric generator, you call it.
So yeah, I guess we have multiple types of symmetry. So in that one, in this case, we did not use that. So there are also multiple parts of the proof where we use the reversibility of the semigroup, and that's where the symmetric
So not at this point.
Yes, but we have like different types of symmetry. So in this case, like these random variables are scalar valued random coefficients, which are simply indexed by the generating set. But here, the symmetrization has more to do with the distribution of these variables than the symmetric properties of the group. So the first step, we can exploit the exchangeability of these random variables in order to insert random signs into this expression the way that we would be able to if they're independent, and apply Rademacher type, which essentially allows us to move this expectation and norm inside the sum. And now this means that we're no longer working with a sum of dependent random variables, but we can work with each of these terms individually. And in that case, we still have to do more work. So the second step is to control the moments of delta st. And this is where the interpolation technique is useful, because we can use different techniques and different time regimes. So for small t, we use Mira curvature. So yeah, maybe I won't write too many details here, but so the idea is at the small t regime, so our random walk, we can think about it started at some point in the group, and at small values of t, our random walk has only made a few jumps, and so its behavior is really dependent on the local properties of the group. And this is exactly what curvature, and in particular Mira curvature, which is a notion of curvature for Markov semigroups, which in the continuous setting corresponds to Ricci curvature, but also has an interpretation in the discrete setting. So this tells us something about the local structure of the group and how the random walk will behave on a small time scale. And in this area of gamma calculus, where this notion of curvature is used, there are many techniques and identities which we can use in order to obtain bounds on these quantities which are coming from the heat kernel. So that's what we use in the small t regime. And for large t, we surprisingly use mixing time results. So in fact, like the classical paper of Kones and Shashikani from 82, sorry, I don't remember the year, but so this is the classical paper which introduced the idea of cutoff in the Markov chain literature, where they prove a result about the mixing of the random walk on the symmetric group with the set of all transpositions as generators. So in that literature, they talk about this as card shuffling. So it's the shuffle where you have a deck of cards and you shuffle it by taking two of the cards and switching them at random. And so here you get very precise bounds, which we do not actually need in that precision, but on how fast the deck will mix depending on the size of the deck. And this is what gives us well-decaying bounds as t gets large. So by using a combination of these techniques, we're able to get this constant. So the log n that's appearing there is actually coming from our use of the mixing time bound, because the mixing time is like 1/2 n log n, and we think that this factor can actually be removed, but that would require more work working specifically with like Markov chain mixing. So yeah, maybe since we have experts here on that, like there would be some interesting questions to discuss. So yeah, I think I'll end there.